Imagine a world far, far away. It is called Pathology Land. Everything is good in Pathology Land. The slides arrive on time, cases are signed out within the required TAT, difficult cases are shown around. Everyone is happy. Then one day, there is a rumor. A new technology is arriving, it says. A technology that will change how Pathology Land operates. It will upend the lifestyle. It may even replace some or all pathologists. It is inevitable, and there is nothing that can stop this technology. For those watching at home, what technology do you think I'm talking about? Yes, I'm talking about immunohistochemistry. In the 1980s, when immunohistochemistry came in regular use, there initially was a lot of pushback. Many pathologists who had not been trained in immunohistochemistry did not want to use it. They did not understand the value it added, and they were not fully on board with the idea as is. 40 years later, it is hard to find pathologists who do not use any IHC in their routine practice. Another new disruptive technology that took off in the 1990s was molecular testing, and that is also commonplace today. The unique thing about human beings is that we adapt, we learn, and we are capable of change. Another example may be smaller in scale, but within pathology, is that of the caseload for liver pathologists. Back in the 80s, 90s, and the early aughts, the majority of medical liver sign-out was viral hepatitis cases, hepatitis B and C. Today, however, a majority of medical liver sign-out is metabolic diseases such as NASH. Outside the world of pathology, the radio industry feared that TV would put them out of business. As we all know, it did not. And TV feared that internet would put them out of business. It did not. Bottom line, things change. We just have to be ready for that change. I'm sure you've seen this photo before. It is no different than this process. My name is Abdul Abid, and I'm a private practice pathologist. I'm interested in cytopathology, GI pathology, and digital pathology. I took an online course from Duke University on Introduction to Machine Learning. However, I'm not an expert in this field. The question, will AI replace pathologists, has been asked for the last 10 years, and I want to share some of my thoughts about this topic with you today. I do not have any relevant financial disclosures. In this presentation, I will talk a little about the evolution of artificial intelligence, how it is being currently used, what lies in the future, and the challenges faced by AI. I started preparing this talk 6 years ago, and I have been bamboozled by new advances in the field. The intended audience of this talk is medical students, pathology trainees, and practicing pathologists who are curious about digital pathology and AI. Starting off, let's begin by some basic definitions of what is artificial intelligence. Artificial intelligence is computers acting like humans. The American Medical Association recommends using the terminology augmented intelligence to make people less afraid of machines. I will use AI through the presentation to avoid taking sides. I also want to clarify that since AI has become so popular in the public imagination recently, a lot of things that are not AI have been lumped under the label of AI. It is like a fad. For example, the autocorrect feature on your phone or chatbots, these are not really AI, according to the scientific discourse. Machine learning is a part of AI that deals with building algorithms. An algorithm is a sequence of instructions used to solve a problem. Us pathologists use algorithms in our mind every day. Is this cancer or not? Is this cancer squamous or adenocarcinoma? Is there lymphatic invasion or not? Is the stain positive or negative? Deep learning is a part of machine learning that mimics human brains. To understand the difference between these three terminologies, we should look at their hierarchical relationship as depicted in this Venn diagram. The next frontier in the lineage of AI is foundation models and then generative AI. There is an excellent paper on this topic published in Human Pathology last year by Dr. Pentanowitz, which sheds more light on this topic. Some of you may be familiar with the British guy on the right. However, it was the British guy on the left who was sort of a prophet of artificial intelligence. His name was Alan Turing, and he wrote that an autonomous machine must be able to show intelligent behavior that is indistinguishable from human behavior, also known as Turing's law. The phrase artificial intelligence was coined at a workshop held in Dartmouth in the summer of 1956. Afterwards, the terms machine learning and deep learning were coined. The Mycin expert system, developed at Stanford in the 1970s, was the first iteration of using AI in healthcare. It was used to identify bacteria causing serious infection. So how does machine learning work? I'll briefly talk about some of the underlying concepts. At the heart of machine learning is the idea that we are going to teach a machine to learn. For that to happen, we give the machine examples, which are data samples, and we want the machine to make predictions based upon that data. The goal is to take a training set which contains data denoted here by X and the outcome denoted here by Y. What we want to do is to build a predictive model that is capable of predicting Y if we provide the model with X. So for example, we provide pixelated images of prostate biopsies with and without cancer, and we label them Y1 or Y0 based on if they have cancer or not. We provide these examples or training set to a machine or an algorithm, and we teach the algorithm which image corresponds to which outcome. The goal is for the algorithm to learn what does cancer look like on a pixelated image. One widely used example of machine learning, if you have an iPhone, the weather app tells you chances of rain at a particular hour on a particular day. The app is able to do it based on past parameters that have been fed into an algorithm, and then it predicts chances of rain at a given moment. Coming back to pathology and image analysis. The way algorithms learn about images is through a process called convolution. At the bottom left is an example image. It is a collection of shapes. What we would like to do is to start at the bottom of our hierarchy and look for one of these shapes or atomic elements. The yellow triangle that you see on the bottom right is one of our atomic elements. We are going to shift that triangle to every location in the image. And our aim is to calculate a correlation which measures how similar the local region in the image is to our atomic element. On the top is the output of this process. When the triangle lines up with a point in the image where the triangle is actually manifested, we get a higher correlation or a high match, which we get in the form of a heat map. The process by which we shift the triangle to every location in the image is called convolution. The overall process or architecture through which that happens is called a convolutional neural network, or a CNN. When you convolute multiple filters, you get a stack of feature maps. You can see that as we move up in the network, we keep adding more and more figures to the equation, and at the end we get a classifier or a probability. That is actually quite similar to how we learned pathology during our training. As med students, we learn basic histology and then some pathology. As a first-year resident, you start with some features until you see enough cases and you keep adding more and more and more filters in your brain. In the real world, pixelated images are not composed of these shapes. What we can use is something called Gabor functions, which act as layer 1 filters when we use them in image detection. We found those filters by shining light on the retinas of mammals and seeing which neuron is turned on. This is a simplified way of how neural networks work. You can learn it this way as well. For using AI in pathology, we can not only use histology images, but also lab data, free text reports, synoptic reports, and molecular data that we have, and we can use it for building algorithms. This approach has been called computational pathology, where we can use relevant information from the patient's chart and histologic findings and provide a more robust diagnosis. This is not yet a reality, but once we reach this stage of evolution on pathology, it will change the way we practice. The first step, however, to get there is digital pathology. Digital imaging or whole slide imaging has been in use for at least 20 years now. Once we have digital images, they can be annotated and then used as a training data for algorithms to give us the result. I was skeptical a few years ago that we'll have widespread digital pathology adoption in the United States. But winds of change brought on primarily by COVID-19 have altered the landscape. Many academic institutions are moving towards or have already adopted digital sign-outs. Even some of the largest private practice groups in the United States have gone digital. I was recently on the interview trail, and many practices of varying sizes are planning to go digital in the near future. Now that I've talked about the basics of AI, I want to show how AI is being discussed in the pathology world. Starting at UPMC, where I spent a year of my fellowship, they have algorithms for image analysis, for quantifying Ki67 immunostain, for recognizing mycobacteria, for quantifying CD8 immunostain, and IBEX for prostate cancer detection. This is a prostate core biopsy from a 60-year-old patient. The IBEX-Galen algorithm highlighted areas which most likely contain cancer, thus narrowing down the relevant area for look at in this image. It also provides a preliminary report. Outside UPMC, there is a lot of research being done on the use of AI in pathology. I recently heard an expert say the other day that there is at least one article on the use of AI in pathology in every issue of Modern Pathology. I think that's true for every pathology journal these days, be it the Archives, AJCP, or even big-name journals like Nature, Science, or New England Journal of Medicine. The number of papers about AI has grown exponentially in the last 10 to 15 years. So has the share of jobs that require AI skills. Billions of dollars are being spent to develop AI for healthcare settings. Another way to look at increasing involvement of AI in pathology is through public challenges. A public challenge is a free-to-public image task, for example, mitotic figure counting or detection of metastatic tumor foci in lymph nodes. An annotated data set is provided as part of the challenge, sometimes as a single set and sometimes divided into training and testing sets. The training set is used to build the algorithm, whereas the testing set is used to evaluate the performance of the algorithm in an independent set of cases. Out of the 191 challenges submitted until November 2019, 12% were related to pathology or combined radiology pathology. Within pathology, the majority was related to breast pathology. If you want to look at more recent public challenges, you should search for Panda Challenge for prostate cancer detection and Chameleon 17 for breast cancer detection. Last year's USCAP conference had almost 50% of companion society meetings and other free sessions dedicated to artificial intelligence or people arguing against artificial intelligence. One of the earliest uses of AI in pathology was in prostate cancer, and Page's algorithm is now FDA approved. However, there is a caveat to the FDA approval. The tool can be used after the case has been seen by a pathologist first. It is not approved for screening benign biopsies, and it can only detect acinar-type adenocarcinoma, nothing else. Since then, there has been progress in the fields of breast pathology, GI pathology, clinical chemistry, hematopathology, calculating PD-L1, even cytopathology. And most intriguingly, in unstained slides. Companies out there are offering algorithms that can predict mutations from histology using AI, be it the MSI status or KRAS mutations in lung cancer. And these are just a few examples of the emerging use of AI in pathology. There's a lot more beyond the scope of this presentation. And it's not just us pathologists that are affected by this, by the way. Remember that radiology has been dealing with AI way before pathology has, and we can learn a lot from their experience, and I will talk more about that later. You may have seen these headlines in news articles in the last few years. But this is not a new phenomenon. It has been shown since the 1950s that machines are better than humans in performing certain tasks. But what if we combine the two? What if instead of pitting them against each other, we look at collaboration? The outcomes are better than doing things separately. Right now, what we have is a pathologist in the loop system with AI functioning to supplement pathologists' decision making. AI is expected to efficiently handle the dull, dirty, or dangerous jobs. Meanwhile, the pathologist remains in control of the AI system, so in the loop. Currently, AI and algorithms are supposed to make practice of pathology more efficient. The next step in the near future will be pathologist on the loop, which means the AI will be capable of independent decision making without a pathologist's input. We are not there yet. What we have right now is narrow or thin AI. It can only do specific tasks. It is not a general AI, which can potentially be autonomous. It is not only task specific, but it is also blind to any other diagnosis on the slide. This is an almost identical slide from a presentation by a radiologist. I really like this slide from Dr. David Rim's talk at USCAB, reminding us that pathologists are not simply readers of slides that can be replaced by machines that are reading slides. We are much more than that. Now let's take a look at the darker side of AI. Turns out human beings are actually pretty smart, and we tend to overestimate AI. All technology comes with a cost. That is a universal truth, especially in healthcare. I'm not a big skeptic, but we should think what are the downsides of an overemphasis on digital pathology and AI. Digital pathology is not perfect, and in the gaming world, there is this phrase, mistakes were made. These are some slides that I had when I was a trainee that were not properly scanned. And I don't know if you can make a diagnosis. I could not. I showed you how IBEX's Galen algorithm works on prostate biopsies, but again, there are pitfalls. GU pathologists who have used those algorithms report overdiagnosis, missed cases, and other issues with the algorithms. Broadly, these are some of the problems with AI, as they are with other technology. Firstly, it will need to be updated frequently with advancement in knowledge. Secondly, like any other machine, AI will get worse with time, so we'll need to come up with QC methods like we do with machines in our chemistry labs. Lastly, who gets to decide what is accurate? In hematopathology, do we follow the WHO or do we follow the ICC classification? And AI is not perfect. There are many things that can go wrong with AI. You may have heard the phrase GIGO, garbage in, garbage out. Another issue with AI in pathology is that we have been trying to fit AI into our existing workflow instead of coming up with something unique. And I think that is, in my mind, one of the biggest issues with the way AI is being developed right now, is that we are trying to fit what we have already, and we're not thinking about how we can modify our current workflows. There is an excellent paper called 21st Century Pathology Workflow that deals with this topic. An adversarial attack can derail AI very easily. Let me present another example. This is a news story from 6 years ago, and I'm sure all of you have had read about this. Go is a popular game in South Korea, and it is increasingly hard to learn. So when DeepMind's AlphaGo beat the world champion, it was considered a new era in the superiority of AI, and there was a lot of hype around this news. However, this story from February 2023 did not make as much of a splash as the first one. This guy, not a world champion of Go, was able to beat DeepMind just by using adversarial attacks. Overfitting is when the machine learns specific answers to general questions and then keeps repeating those. When there's automation, users tend to think, don't worry, I'm sure the machine will catch me if I make a mistake. This, however, does not always happen. Anyone who has ever used a dictation software or Epic can tell you horror stories about this. What we need is more transparency and less black box type stuff. I believe explainable AI is one model to address that problem. Explainable AI aims to explain the reasoning behind decisions taken by the algorithm. It's like adding a Y button to the algorithm. Like one of the slides I showed earlier, when dealing with digital pathology, we have to think about pre-analytic factors before we subject our cases to machine learning. This is a nice paper on the limitations of machine learning, highlighting the narrowness of AI. Like I mentioned earlier, our colleagues in radiology have more experience in dealing with AI. This is an article from the magazine Quartz from June 2021. By that time, more than 80 algorithms were cleared by the FDA for use in radiology. But radiologists were not using them frequently. The reason? Inconsistent performance. This is a quote from Andrew Ng, AI guru and founder of the website Coursera. This is also from the Quartz article that I just mentioned. And I want to draw your attention to the last line where he talks about the gap between developing AI algorithms on datasets and real life use. Another example is the KI detection software that I mentioned earlier. That AI model actually overcounts compared to the manual counting of Ki67 in breast cancer cases. And did you know that AI can hallucinate as well? Hallucination in this context is when an AI makes things up. It is easier to trick a machine than it is to trick most humans, since AI does not really know what cancer is. It can be trained to look at different types of cancer, but there is no common sense behind it. A large language model like ChatGPT, for example, does not understand what a fact is. This is a Gartner hype cycle, and you will see it in almost every single presentation on AI that you ever see. Right now, I think we are at the peak of hype in AI. Actually, I think we are a little bit down now, since some people have compared, like maybe around here. Some people have compared it to internet in the time just before the dot-com bubble in the late 90s. Lots of promise, not much durability. A survey was done by the CAP's AI committee, and it found that most pathologists are not comfortable using AI tools. This is not great news, because pathologists should be more involved in designing these algorithms like our radiology colleagues. Otherwise, the algorithms will be poor in quality and not useful. As an example, I showed the number of public challenges using data sets earlier, and the highest number of challenges were in breast pathology, followed by surgical pathology. However, in routine practice, most general surgical pathologists see more GI and GU cases in breast and cervix. Many people argue that AI is being developed too fast and without taking into consideration the possible downsides. And it's not just tech leaders, but also physicians who are warning about AI. Some of this feels like scaremongering, but the true impact will lie somewhere between the terrifying robot overlord extreme and benign, helpful machines. I think this is the most important question that any company trying to develop pathology-related algorithms should ask. If you had to delegate any tasks that you find cumbersome in your daily practice to someone else, which tasks would that be? I'll give you an example. I don't like looking at AFP stains to hunt for mycobacteria. Many people don't like counting mitoses. Then there is the administrative burden that we need help with. Is AI being developed to help with those issues? Now that I've talked about various aspects of AI, let's talk a little bit about how I foresee pathologists integrating AI in our daily practice. Right now, this is what the typical workload for pathologists look like. This is our typical work day. We do a lot of triaging. But what if we had an AI assistant that sorts this out for us? Imagine you come into work one day and your AI assistant, let's call her Tabitha, has already sorted out the cases for you. Wouldn't that be awesome? It could be like a digital fellow, and you may not need any more surgical pathology fellows, which makes me sad to think. This is a more realistic version of that from the IBEX team. In this example, you see cases that have been triaged by the algorithm, and you may get your stains the same day as well. Another version of this is for AI to determine regions of interest in each slide if there is tumor. And then it should pull up any prior malignancies seen in that patient, and then once the pathologist agrees with those AI, the AI will compile a final report. I think a fundamental question that we have to ask ourselves, not only with AI, but with any new technology, is what problem is this fixing? The American College of Radiology has a dedicated data science institute that puts out use cases for potential algorithms. I think that effort is worth emulating, guiding the advent of AI instead of being a mere follower. For example, let's look at this use case for a potential algorithm for detection of acute appendicitis. It provides parameters that should be part of the potential algorithm. AI was supposed to spell doom for radiology, but look at the trend of med students matching in radiology in 2023. And also the job numbers for radiology in the last few years seems like the opposite of doom to me. Coming back to pathology land and its future. What if in the future you don't even need a microscope or a standard office desk? This is me 20 years from now signing out a benign breast lesion that has already been triaged for me from the future. To answer the existential question, AI will most likely not replace pathologists. Your jobs are safe. All we need is a transfer of skills. In fact, why don't we ask AI about it? As you can see, even AI knows how difficult it will be to replace pathologists. These are some of the resources that I utilized in preparing this talk. I leave you with some free resources to learn how to code and use machine learning. If you want to read in detail any of the papers or news articles that I have mentioned in this talk, you can scan this QR code and get the links. Thank you very much for your time, and please let me know if you have any comments or questions.